All right, so we are done with thermodynamics and we're going to get started with optics. So the first chapter on optics is chapter 33. And chapter 33 has to do with the nature and propagation of light. Light has a dual nature behavior. Light can behave as a particle. It can also behave as a wave. Okay. Newton supported the idea of the particle behavior of light, and it was recognized for a long time. But then key experiments done in the 19th century confirmed the wave-like behavior of light. So in the 19th century, they did some interference experiments that confirm the wave behavior of light. Okay. Finally, in the 1930s, developments in electrodynamics reconcile both behaviors of light, the particle behavior and the wave behavior. So in 1930, developments in electrodynamics reconcile both behaviors of light. Okay, so for now, in these next chapters, we are going to talk about or concentrate in talking about the wave behavior of light. Uh, Eventually, we are going to also discuss the um, particle behavior of light. Okay, so a couple of things in here. First thing we need to get out of, put it right out, is that the speed of light. Okay, so the speed of light in vacuum and also considered to be the speed of light in air is labeled as c is equal to 3 times 10 to the 8 meters per second. Okay, this is the value that we are going to use. Okay, our next topic here is going to be waves, wavefronts, and rays. And rays. Okay, now consider the waves created by a rock when it's dropped in a lake. The waves created will form a concentric outward moving circles. Basically, what you're going to see is you're going to see this, the wave moving as circle propagating into a circle. Okay. These circles are what I would refer as the wavefronts. Okay. And the radial motion of the waves indicated by upward pointing arrows are called the rays. So if we think about the source being here and we use some imaginary, these are imaginary arrows that represent the upward motion of the waves. Okay, so let me draw those. Okay, remember these green lines that I'm drawing right now, they're imaginary lines. You don't see this. You ever throw a rock on a lake, you notice that you don't see the green lines, but you do see the blue ones, which are the wavefronts. We call these rays. And we're going to use rays. They're going to be very important in chapter 34 for us. Okay. The rays are always perpendicular to the wavefronts. Okay. So basically what we have in here is that this is always a 90-degree angle. Okay. And rays are graphical representation. They are not real. So rays are graphical representations. They are not real. Okay. Now, our next topic in here, these are just definitions that we're discussing right now. We're going to get into how to use them in a few minutes, or maybe in the next video. Now, our next definition is that of plane waves. Now, imagine as these waves travel and travel and they travel far away, then eventually the radius of the curvature of these waves, this radius right here, will start getting bigger and bigger and bigger. And when you look at this distance to be infinitive, now these lines don't look like they are curved, but they actually look straight. So as the waves travel away from the source, uh, because they become less circular and more like a straight lines. So let me write that down for you. As the waves travel away from the source, okay, they become less circular and more like straight lines. Okay. At this point, the waves are considered to be plane waves. The waves are considered to be plane waves. Okay. And they are still perpendicular to the rays. So basically what this looks like is our waves are going to look straight. So this right here, this is our plane waves. And we still have our rays, but because we're far, far away, now these rays are parallel to each other. So these are our rays. And still, the waves and the rays are perpendicular to each other. Okay, so these are our place waves. These place waves, these are what originally were our wavefronts. And now they're considered to be plane waves. Okay. The next topic in this chapter is on section 32.2 or 33.2, excuse me. So section 33-2 is reflection and refraction. Okay. When light hits a smooth boundary between two mediums, two events take place. Okay. So when light hits a smooth boundary between two surfaces or two mediums, two things take place. Okay. Part of the light is going to bounce back from the surface. Okay. So part of the light will bounce back from the boundary. Okay, and this is what we call reflection. Number two, okay, part of the light is transmitted. Part of the light is transmitted through the boundary okay, from the first medium into the second medium. And this is what we call refraction. Okay, so remember, the bouncing from the smooth surface is what we call reflection, and the transmission of the light through the boundary from one medium to the other is what we call refraction. Okay, so let me bring in a picture for you here. Okay, this is in your PowerPoint. This is on slide 6 on your PowerPoint. Okay. So as you can see here, this is your incident rate. This is the incoming rate. It hits the boundary and it bounces back. And this is what we call the reflected rate. This is the reflection taking place. And some of the light goes through, and this is what we call the refracted rate or refraction. This is boundary A, and this is boundary B. We could be coming from air into water, for example. Okay. The directions of the reflected and refracted rates are measured using the angle the rates make with the surface normal. And the surface normal is a perpendicular line to the boundary. Okay, so let me write that down, and then we're going to go back and look here at the picture. So the directions of the reflected and refracted rates are measured using the angle the rates made with the surface normal. Okay, and the normal is a perpendicular line to the boundary. Okay, so let's take a look at this. So the directions right here are measured with respect to this angle, but notice that this angle is measured right here from this line. And this line, which is our normal, is a 90 degrees with respect to the boundary. And theta sub b is the direction of the refracted angle. Theta r is the direction of the reflected angle, and theta sub b is the direction of the refracted angle. In this case, theta sub a is the angle of incident. That's the angle in which the light came into the boundary, and is also measured with respect to the normal. So always remember that we measure the angles with respect to the surface normal. And the surface normal is a line that is perpendicular to the surface or the boundary between the two medians. Okay. Our next topic in here is what we call the index of refraction. Okay. And as light goes from one medium to another, the speed changes. Okay. So as light goes from one medium to another, its speed changes. I don't know if you noticed when we were talking earlier, and I say C is equals to 3.10, 3 times 10 to the 8 meters per second. I made sure that I mentioned this was the speed of light in vacuum, or in air is also close to the speed of light in air, that we call it to be the speed of light in air. Okay, but that speed, that 3 times 10 to the 8, is restricted to those two mediums. If we have light traveling through water, the speed will be different. Okay, so in vacuum, as we were saying, in vacuum and air, C, the speed of light, is 3 times 10 to the 8 meters per second. In air, it's a little bit slower, but we can't sort of ignore that and make it and just assume that it's about the same as is in vacuum. Now, the speed of light in other mediums will depend on the characteristic of the medium, and it will always be less than C. Okay. The speed of light, as we will discuss when we get to relativity towards the end of the semester, is the maximum speed that we have. The 3 times 10 to the 8 meters per second is the fastest anything can go. Nothing can go faster than the speed of light. So as the light enters into a medium that is no vacuum or air, it's going to slow down. It's not going to speed up. And how much it's going to slow down, how much its speed is going to be, is going to depend on the material itself. Okay. The ratio of the speed of light in vacuum to the speed of light inside a medium is what we call the index of refraction. Okay, so the ratio of the speed of light in vacuum and through another medium is called the index of refraction. Okay, and the index of refraction is represented by the letter N, and it has no units. Has no units, and is always bigger than 1 for mediums that are not air or vacuum. For air and vacuum, n is equals to 1. Okay, so n is just going to be the speed of light divided by v. So n is the index of refraction. C is the speed of light in vacuum, which is a 3 times 10 to the 8 meters per second. And V is the speed of light, in the material. Okay. So in air, for air, n is actually equals to 1.0003. But we assume that it's equals to, we approximate it to be equals to 1, which allows us to say that the speed of light in air is equal to the speed of light in vacuum. Okay. For other surfaces, let's say for water, it's about 1.333. Okay. We will discuss more this in more detail because we're going to be looking at how the behavior of the light that goes to one medium from air into another medium, in how this affects different things. Okay, our next topic here is the law of refraction. And this is very simple. Okay, it's a very simple law. The law of reflection, it states that the angle of the incident and reflected rate are the same for all light wavelengths and materials. Okay, so this law states that the angle of the incident and reflected rates are the same for all light waves and materials. For light wavelengths and materials. Okay, so let me bring you a picture here. Okay. Again, here is your incident rate, here's your reflected rate. What the law of reflection tells me is that the theta A is equals to theta R. Okay. where theta A is the incident angle and theta sub R is the reflected angle. Okay. And it doesn't matter what the medians are, this will always apply. These two angles will be the same. Okay. Next, what we're going to look at is going to be types of reflections. Okay. And we are going to discuss two types of reflections in our case. Okay. The first one is called the specular reflection. Okay. And this is the reflection from a smooth surface. Okay. The reflected rays are parallel to each other. Okay, so let me bring you a picture. This is again is from the PowerPoint to slide 10. So here, this is a smooth surface, both of them. And as you can see, the rays are parallel to each other. Here's are your reflected rays, and they're all parallel to each other. Okay. In your book, all the reflections that we're going to discuss are going to be specular reflections. Okay, so that's what we're going to discuss in this book. The other one that we have is what we call the diffuse reflection. Okay, and in a diffuse reflection there is a reflection, excuse me, from a rough surface. Reflection from a rough surface. Okay. Here we must consider reflections for all the irregularities. See? So all reflections from the irregularities of the material of the surface must be considered. Okay. The reflected rays will travel in a variety of directions. Okay, most objects are visible to us because of this type of reflection. Okay, and let me bring a picture for that real quick. So here is, notice in this picture, and now we have these little hills and valleys. And when you hit, when the light hits those hills and valleys, the bouncing of the reflected rays is going to be so kind of random, and the rays are not parallel to each other. So reflected rays are not parallel to each other. Okay. Like I said, most of the stuff that we look at, uh, the objects that we are able to see are due to the fact that we have this diffuse reflection. Okay. Our next stop here is going to be the law of refraction. Okay, we talk about the law of reflection. Now we're going to talk about the law of refraction. Okay. So two materials with indices of refraction equals to N1 and N2. Let's say we have, let's have so two materials with indexes of refraction N1 and N2. Okay. So for two materials, so for two materials with indices of refraction N1 and N2, the incident angles and the refracting angles are related by Snell's law. Okay, the incident angle and the refracted angle are related by Snell's law. Okay. So let me bring you a picture of the angles that we're talking about, and then we're going to write down Snell's law. Okay, so theta sub A is our incident angle, and theta sub B is our refracted angle. And these two are related by Snell's law. We can say that N1 is the index of refraction from the incident side, and N2 is the index of refraction for the refracted side. Okay, and your book uses A and B instead of B and A. So let me adjust this. In the PowerPoints, I am using A and B. So let me change this. So instead of calling this N1 and N2, I'm going to call it NA and NB. And the funny thing is that when you are going to do the problems in the homework, they are labeled as N1 and N2, no NA and NB. But just remember, is one is the index of refraction from the incident medium, and the other one is the index of refraction for the refracted medium. Okay, and Snell's law just tells me that the product of the index of refraction of the incident medium times the sine of the incident angle is going to be equal to the index, the product of the index of refraction of the refracted medium times the sine of the refracted angle. Okay, this is Snell's law. Okay. It's going to be useful for a couple of things later on that we're going to discuss. Okay, so again, n sub A is the index of refraction of the incident medium so meaning the incoming light. Maybe that helps, makes it a little bit more clear. Of course, theta sub A is our incident angle. Okay, and these angles are measured in degrees in case is there any doubts. They are measured in degrees. Okay, and these are measured from the normal, remember. N sub B is the index of refraction of the refracted medium. Okay, so I guess this is the light that went through. Okay, and of course theta sub B is the refracted angle. Again, measured from the normal. Okay. Snell's law reads the same whether light begins in the substance with the larger or the smaller index of refraction. So it doesn't matter whether you're going from a small index of refraction into a bigger index of refraction or from a big index of refraction into a smaller index of refraction, the law reads the same. It's going to be the product of the incident, the index of refraction of the incident medium times the sine of the incident angle equals to the product of the index of refraction of the refracted medium times the sine of the refracted angle. Okay. There are three cases to consider in here. Okay. And what I'm going to do, instead of writing those down, I'm just going to copy the slide because, you know, there's no more that I can add to that. So Snell's law cases. Okay. There are three cases to consider. Okay. So let me just bring this in. This is slide 12 on your PowerPoint. Okay, so case number one. A ray entering a material of larger index of refraction bends towards the normal. So ray entering a material of larger index of refraction bends towards the normal. So if I were to draw this, case number one, I'm gonna try to fit everything in here. So case number one, if I were to draw this, this is my boundary. Here's my normal. And I have my ray coming in. This is theta sub A. The refracted ray is going to bend towards the normal. This would be theta sub B. So the refracted ray will bend in this direction. Okay. Case number two, a ray entering a material or smaller index. So here, let me put this as NA is, so the index of refraction bends entering a larger index of refraction, so NA is less than NB. Okay. So case number two, a ray entering a material smaller index of refraction bends away from the normal. So again, here's my boundary. This is my normal. I have my ray coming in. Okay, this is theta sub A. And now theta sub B is going to look like this. So here we have NA is greater than, excuse me, NB. So you're going from a higher index of refraction to a lower index of refraction, and the ray will bend away from the normal. In the case of a normal incident, meaning the incident angle is equal to 0, the transmitted ray will not bend. Okay, so number three, in the case of an incident angle that is a normal incident angle, then the ray will not bend. So let me just draw this for you. So here, this is case number three. Here's the surface. Here's the normal, once again. So an incident ray that is normal will mean the ray is coming in this direction. Okay, and theta sub A will be equals to 0. And what will happen is the refracted ray would be the same here. So theta sub B would be equals to 0, regardless of what NA or the relationship between NA and NB. Doesn't matter which one is bigger, which one smaller. Regardless of that, if the ray is perpendicular to the surface, okay, it's 90 degrees to the boundary, meaning that is 0 degrees from the normal, because remember the normal is perpendicular to the boundary, then the angle will not bend. Okay, so hopefully that this makes sense. All right. We're going to talk about the index of refraction of a wave and the wave aspects of light. That's our next topic. Okay. When we look at the situation going from one material to another, okay, we realize that, we discussed that the speed of light changes as we go from one material to another. regardless of whether we're dealing with light or we're dealing with any other, or we're dealing with different materials, we know from chapter 14 and 201. So let me think, did you cover this in chapter 14 and 201? I don't recall if that's actually, I don't think that's covered in chapter 14 and 201. I think for you guys to think about this, you have to go back a little bit further, which is going to be in the 100 level classes. So in case you don't remember this, let me just write it down. For any material, or type of wave, and when you guys discuss this in the 100 level classes, you discuss it for the point of view of sound waves, not light waves. The speed of a wave is given by V is equals to lambda times F, where V is the speed, lambda is what we call the wavelength, and you do discuss wavelengths in chapter 14, that I remember. Wavelength is in meters, and F is the frequency. And the frequency is in hertz. And a hertz is nothing more than 1/2. Okay. So as a wave passes through one medium to another, something very particular happens. The frequency of the wave does not change. The frequency of a wave does not change as the wave goes from one material to another. What this means is this includes light. So when it comes to light, the frequency of the light will not change, but the speed will change. And since the speed is the product of the frequency times the wavelength, in order for the speed to change while the frequency is being kept constant, the wavelength has to change. Okay, so that gives us a very interesting situation. So if we're in air, I will have that the speed of light in air is going to be the wavelength in air times the frequency of the light. And then let's say I go into another medium, and that medium, it could be water, could be anything. It's going to have a speed v, and this is going to be the frequency in the medium, excuse me, the wavelength in the medium times the frequency. Remember, the frequency does not change. So if I take a ratio of these two equations, okay, if I divide them by each other, I'm going to get C over V is equals to the wavelength of air over the wavelength of the medium. Times frequency, and frequency and frequency will cancel out. Now recall that C over V is equals to the index of refraction N. So that will mean that N is equals to the wavelength of air over the wavelength in the medium. Which means that the wavelength in my medium will be equals to the wavelength in air divided by the index of refraction, where the index of refraction is bigger than 1. So that means that your wavelength will reduce as you enter another medium. In your book, The wavelength of air is labeled as lambda sub zero. Okay, it's not the wavelength. The wavelength of light in vacuum in air is labeled as lambda sub zero, and the lambda in the medium is labeled just as lambda. So from your book, in your book, the equation is lambda equals to lambda sub zero over n, where lambda is the wavelength of light in a material. Okay. And most of the time, this is measured in nanometers, which is 10 to the minus 9 meters. Lambda sub zero is the wavelength of light in vacuum, but also in air, also measured in nanometers, which is 10 to the minus 9 meters. And of course, n is the index of refraction. Of the material. And remember that n is greater than 1. It's equals to 1 when you're in air, but it's greater than 1 when you are in another medium. Okay. So that's the relationship that we get for the wavelength when the light goes from one medium to another. Okay. And we're going to make use of this, also this idea here further down the chapter. Our next section is section 33.3, and we're going to kind of stop at that point. So I'm going to cover this, and then that's where we're going to stop this video. So 33-3 is called total internal reflection. Okay. So let's consider the case where the light is incident from a side with a larger index of refraction. So it's coming from a larger index of refraction to a larger, to a smaller index of refraction. Okay, so let's consider that NA is greater than NB, and therefore theta B will be greater than theta A. Because remember, when you go from a larger index of refraction to, let me see, let's go back here to show you that. Okay, when we're going from a larger index of refraction to a lower index of refraction, the light bends away from the normal, meaning that theta B is going to be bigger than theta A because you're going away from the normal. So in this case, and what we're doing, because we're coming from a greater index of refraction to a smaller index of refraction, the angle of refraction will be greater than the angle of reflection. Okay, so since the refractive rate is bending away from the normal, okay, in this case, as you make theta sub A larger and larger, theta sub B is going to go farther and farther from the normal. And the rate of theta sub, or the refractive rates are going to get closer and closer to the horizontal. So as we increase theta sub A, the refracted ray will move closer and closer to the horizontal. Okay. So as this happens, eventually theta sub b will reach 90 degrees. It will be perpendicular to the normal. And the ray will be parallel. Okay. The ray will be perpendicular to the normal, will be parallel to the horizontal, and the value of the incident angle in which that happens is what we call the critical angle. Okay, so eventually theta should be, will be perpendicular to the normal. And we're going to do a lap on this. Okay, and so what you have in here, if I draw my boundary here, and I have my normal, I have a particular angle, theta sub A, that will make my theta should be 90 degrees with respect to the normal. Okay, and this angle here, I shall share, this angle here, okay, the angle at which the incident angle at which the refracted angle okay is parallel, it's perpendicular to the normal, excuse me, parallel to the horizontal but perpendicular to the normal. Okay, is called the critical angle. Okay, so what do we have? Remember, we have Snell's law that says theta A sine of, not theta A, NA sine of theta A is equals to MB sine of theta B. Okay, so if theta B is 90 degrees, we have NA sine of theta A is equals to MB sine of 90, which is 1. And from there, sine of theta A will be equals to MB over NA. And this sine, this is the sine of our critical angle. Notice from this relationship that for this to work, N sub A has to be greater than N sub B. Okay, because otherwise around, you don't get a sine, because to find the critical angle, of course, you will have to do the sine inverse of MB over NA. And inside that argument for that sine inverse, the value has to be at most 1, and it cannot be greater than 1. Okay, because then you don't get an answer. So this total internal reflection, when the light comes in at a certain angle and the refracted rate doesn't make it, it disappears on the inside median, on the next median only works when you're coming from a higher index of refraction to a lower index of refraction. So NA has to be higher than MB. Otherwise, you will not get this situation. Okay. Now, for angles of incident greater than the critical angle, okay, the beam is entirely reflected at the boundary. Meaning no refraction. Everything is reflection. Okay. All these, in this situation where everything is reflected, okay, this is what we call our total internal refraction. Okay, and it's only possible when you're going from a larger index of refraction to a lower index of refraction. Okay, a mirage is an example of internal reflection. A mirage is formed by total reflection of the light between layers of cold air and warm air. Okay. Let me see what else we need here. This is about where we're going to stop. One last thing. This is in the PowerPoint, in slide 15. We talk about a little bit about fiber optics in there. It's just one slide. It's not much that we talk about it. And fiber optics makes use of this internal reflection. As the beams are reflected, are transmitted to the fiber optics lines, they're internally reflected. You don't want any of the light to come out of the cable because then you lose data. And then the data is in the form of light is transmitted from one point to the other. Okay. Let me just put the picture so that you have it. But like I said, I don't discuss much of it. Okay, so notice how here we have complete reflection at the boundary, nothing escapes. Okay, so there's no refraction, there's nothing going from the outside, from the inside into the outside. Okay, so when the beam light enters one end of the transparent rod, the light can be totally reflected internally if the index of refraction of the rod is greater than that of the surrounding material, and the light gets trapped inside. So notice that we're not saying that you are surrounded by air, because this index of refraction, well, the index of refraction is greater in the material than is on air. So the light gets trapped in there, but these things have coatings on them that have different index of refraction, and those are designed to ensure that the light does not escape the fiber optic cables, because if they do, then you will lose data, because this light traveling through the fiber optic cable represents zeros and ones, which is your digital data that you need to transmit your information. Okay, and all this is done to total internal reflection. Okay, I'm going to stop here. We will continue in another video with the next sections on chapter 33.